All right, today we're going to solve this problem. We have an urn with 3 green and 4 red balls. We draw 3 balls one by one without replacement. Part A asks us to find the probability that the colors we see in order are green, red, green. And part B asks us to find the probability that our sample of 3 balls contains 2 green balls and 1 red ball. Okay, now I want to emphasize that there are multiple ways of solving this problem, and this is just what I came up with, okay? So for part A, and then let me just remind myself. So we have 3 green, 4 red, right? 3 green and 4 red. Three green, 4 red. Okay, so we want the probability that we choose a green, then red, then green. Okay, so the probability that the first ball is green is 3/7. Then once the green ball is chosen, the probability that the next choice is a red ball is 4/6. Do you see that? Once the green ball is chosen, then I'm left with 2 greens and 4 reds. So the probability of choosing a red ball at this point is 4/6. And we might as well simplify 4/6 to be 2/3. Just to make our lives easier. And then finally, once a red ball is chosen, then the probability of choosing a green ball is what? So let's see. So we've chosen a red ball, and so therefore the new probability of choosing a green ball in our third decision, or our third draw, is 2/5. Now you might ask, why do these probabilities multiply together? And the answer is that, how would I explain this? Yeah, so I guess to understand why these probabilities multiply together, it probably helps to first consider a simpler problem. So so let's just go on a side quest here. So why do probabilities multiply like this? Okay, so if I have a coin and it's either heads or tails, let's say, and then I look at, let's say, 3 different coin flips, okay, then essentially, if I want to look at a single event, so a single event in this case would be tails, heads, tails, then, for example, I mean, it doesn't have to be this example, but this single event is actually part of a tree of possibilities. So the tree is, when I flip the first coin, there are 2 possibilities. And then let's say that I want tails to be the possibility that I keep track of. Okay, then I flip the coin again, and all of a sudden, all of these, the branches of this tree branch off into new possibilities. So then this is the heads and the tails of the second coin. And now I have 4 different possibilities, and tails heads is only one of those 4 possibilities, okay? And so notice the multiplication is happening at this branching, okay? So since I have 2 possible outcomes here, and then each branch, each of my 2 branches is splitting into 2 new branches, I have a total of 4 possibilities, namely 2 times 2, okay? So if I look at the tree, which encodes all possible, and then, of course, sorry, I should mention that for the third coin flip, this is going to branch off again. And when it branches off again, then I'm going to have 8 total possibilities. And this single event that I've highlighted in red is a single branch of this tree. And so it's one of 8 equally likely possibilities. And the 8 is coming from that each time we flip a new coin, we're branching off in this tree we're doing another branching process of this tree, and each time we branch off, the number of total possibilities doubles, or it gets multiplied by the number of splittings. So in this case, right, when I pick a green ball, so when I pick the first ball, there are 7 possible branches. So let's draw this out. This is a great, this is a great piece of intuition. So when I draw the first ball, there are 7 possible choices. Okay, so there's your 7 choices, and 3 of them are green, and 4 of them are red. Okay? Now, when I choose the next ball, I have 6 balls remaining, and so out of this branch, okay, so let's focus on this branch here. So on this green branch, I have 6 balls remaining, and 4 of them are red, 2 of them are green. So at the next process of the selection, this branch is going to split off into 4 red branches and 2 green branches. Okay, and then the same thing is going to happen for each of these 3 green branches. Now these red branches are going to split off differently. The red branches are the branches where I actually chose a red ball to begin with. And so the red branches are going to split off into 3 reds and 3 greens. But notice they're still splitting into 6. One branch is getting split into 6 branches, okay? And so at this stage of splitting, we're still multiplying by a factor of 6. And if you recall, this wasn't a 2/3 originally, it was a 4/6. Okay? And so the multiplication on the bottom, this 7 times 6 times 5, is actually encoding the fact that these branches are getting split. I'll do the last branch getting split. So let's consider maybe we wanted a red branch here, the second outcome to be a red branch. So let's zoom in on this red branch. And then at the final choice, my red branch is now splitting into, into 3 possible reds and 2 possible greens, okay? Wonderful. And then the branches that we're considering, so we have this giant tree, which I have not fully drawn. But this giant tree is all the possible ways to choose the 3 balls in order out of our set of 7 balls. And then, so this is the giant tree, and the amount of branches of this tree are precisely 7 times 6 times 5. Okay, so there are 7 times 6 times 5 branches of my tree. Now, if I want to consider the number of branches which go green, red, green. So an admissible branch would be let me just draw it out. So maybe make it in bold or something. So an admissible branch would be this one here, where my branch goes green, red, green, right? That's an admissible branch. So I'm trying to count the number of those branches and then divide that by the total number of branches. When I count the number of those branches, okay, I have 3 at the first stage, and all the other branches die. I don't even need to consider them because they're automatically failed to be the right type of branch. So I look at these 3 branches at the start, and then these 3 branches, each of them branches off into 4 admissible branches. So four, obviously they're branching off into 6 total, but only 4 of those are red, which is what I care about. So each of these 3 branches branches off into 4 red branches, and then each of these red branches branches off into 5 new branches, and I only care about the 2 which are green. So we can see that basically this right here, this is 4 red branches. I have a splitting of 3 green branches, which I care about, and then finally splitting of 2 green branches at the final step. And so this is where the 3, 4, and 2 are coming from in the multiplication of the numerator. Okay, and then yeah, again, to emphasize, the denominators are just the total number of branches. So here's 7 total branches, and then each of these splits off into 6 total branches, and each of these splits off into 5 branches. Okay, so this is an intuitive understanding of why these probabilities are multiplying in the way that they are. And underlying this whole discussion is the fact that our sample space is equiprobability. So each one of these branches has an equal probability of occurring because we're choosing the balls completely at random with a blindfold, for example. So it suffices to find this probability, it suffices to just count the number of branches which agree with this outcome, and then divide that by the total number of branches. Okay? All right. So that's part A. Now let's look at, and we could also do some simplification, I suppose. So let's simplify 4/6 to be 2/3. And then this is 4. These cancel, 4/35. Okay, now let's look at part B. So part B asks us to find the probability that two balls are green. 2 balls are green, and 1 ball is red. Okay. So the naive way of tackling this is just to split this into all its possible cases, which is what I'm going to do, because this is how I would tackle the problem. And maybe you could find a better way of approaching it. And if so, please leave that in the comments. But what I'm thinking is that, we're looking at the probability that 2 of our balls are green and 1 of them is red. So there are 3 possible outcomes. Either I have green, green, and then I choose red. Or I could have chosen green, then red, then green. Or I could have chosen red, and then green, and then green. Okay, so we calculated this probability already. This probability is 4/35. Now let's calculate the other 2. So to calculate this probability, Again, just for my own reference, we start with 3 green and 4 red. So choosing a green initially, I have a 3/7 probability. Then choosing another green, I'm going to have a 2/6 probability. And then choosing a red, I'm going to have a 4/5 probability. Okay? And please verify this on your own. If I draw the same diagram here, again, 3/7 is clear. It's clear that, from this picture, I have a 3/7 probability of choosing green. Now, once I choose that green ball, I'm left with 2 green remaining and 4 red remaining. And so now at the next step, the probability of choosing a green is now 2/6. And then once I choose that green, I'm left with 1 green and 4 reds. And so that leaves me a 4/5 probability of choosing red at the last stage. Okay? And then similarly, by the identical logic, the probability of choosing red, green, green is going to be 4/7 times, then I'll have 3/6, and then I'll have 2/5. And so actually notice that although the numerators are kind of different in all 3 of these calculations. If we let's rewrite the 4/35 into its unsimplified form, which was 3/7 times 4/6 times 2/5. Okay, so notice that that the numerators are all different order, but when I multiply the fractions together, then actually these 3 numbers are identical, right? I just have a 3 times 2 times 4, a 3 times 4 times 2, and a 4 times 3 times 2. All of those are the same number. So all of these are actually 4/35. And so I get 4/35 plus 4/35 plus 4/35, which is going to be 12/35. Now let's take a moment and think about, before we conclude this video, let's take a moment and think about why are these the same number, okay? That's a little bit weird, right? So intuitively speaking, when I choose a green ball, I am reducing the number of green balls in the urn, and therefore I am increasing the probability of choosing a red ball. But in some sense, the green balls and the red balls are disjoint from each other. So when I choose a red ball, right, this is just this number at the numerator here. This number in the numerator is I should color it green. This number is the number of remaining green balls. Okay? So this number only cares about this numerator only cares about the amount of remaining green balls. And the denominators are always going to be 7, 6, 5 because this is just the nature of the count of the experiment itself. The experiment itself is always going to reduce the total number of balls from 7 to 6 to 5. And so the numerators here, they just care about the number of remaining balls of a specific color. Now this is the number of remaining green balls, and then the 4 is the number of remaining red balls. And so intuitively speaking, this requiring my outcome or my event to have 2 green balls and 1 red ball, this is somehow specifying the number of remaining red balls and the number of remaining green balls. In particular, my final configuration is always of the form 1 green ball and 3 red balls. So I'm always going to end up with this final configuration, regardless of if I chose the green balls first and then the red ball, or if I chose, regardless of the order of colors, I always end up with the same remaining configuration, or the same number of remaining balls. And so because of this, intuitively speaking, actually these probabilities are the same regardless of the order, because no matter how I order this, I still have the same numbers of remaining green balls and remaining red balls in the numerator. So that's one way to make sense of it. There's probably a deeper explanation for this that it's not coming to me right now. So this will have to do. But I hope you enjoyed this video. I certainly enjoyed making it, and have a nice day.